So next we are going to consider Newton's law of cooling, and we're going to apply it to forensics. So Newton's law of cooling states that the rate of change here of the temperature, so rate of change is a derivative, so rate of change of temperature of an object is proportional to the difference between the temperature of the object and the temperature of the surrounding environment. So we can, we'll first define our function here. So let's call capital T temperature. So that's really temperature at time t. So that's the temperature of the object here that we're interested in. And then we'll use T sub A as the ambient temperature, so the room temperature. Then to state this relationship, Newton's law of cooling, so the rate of change of temperature of the object, so that's the rate of change of cap T, so that's a derivative. That's dt d time is directly proportional to, so it's a constant multiple of the difference between the temperature of the object, that's T here, and the temperature of the surrounding environment, that's T sub A. So that is Newton's law of cooling written as a differential equation. Well, we can solve this because this is a separable differential equation. So what we want to do is multiply both sides by dt. So we can multiply by dt on the left and on the right. And then we can divide both sides by t minus t sub a. So actually get a 1 over t minus t sub a. So if we do that, then these guys cancel, dt's cancel, and we are left with dt over t minus t sub a, and on the right, k times little dt. So now we've got our variables separated, and I'm just going to leave t sub a in there for the instant, and also k, because we don't have any information about those. So what next? Well, once your variables are separated, you integrate both sides, right? So, well, this integral on the right-hand side, that's pretty easy. That's integrate a constant. You just get constant times t. How about this one on the left? Well, this is t minus a number on the bottom. And derivative of t minus a number would just be 1. So we've got g prime over g. And remember that the integral of g prime over g is natural log. So this left-hand side integral, that is just the natural log absolute value t minus t sub a. Right-hand side, integrate k, you get k times t, combine both arbitrary constants to a plus c on the right-hand side. And now let's go ahead and exponentiate on both sides to try and solve for cap t here. So e to the natural log t minus t sub a is equal to e to the kt plus c. So here e and natural log together, cancellation laws, those guys will cancel out. And then on this right-hand side, when you add exponents, that comes from a multiplication, right? When you multiply, you add exponents. Well, let's do that backwards. So this is the same thing as e to the kt times e to the c, right? We're used to doing it the other way, but we can do that. So in our next step, we've got absolute value t minus t sub a is e to the c, e to the kt. So I brought the e to the c out in front because c, remember, is our arbitrary constant. So e to the c is going to be an arbitrary positive constant. And then to get rid of these absolute values, we introduce a plus or minus sign. So whatever's inside is going to be either the right-hand side or it's negative. So t minus t sub a is going to be plus or minus e to the c times e to the kt. And then this constant here, plus or minus e to the c, we're going to rename that and call it a. So then to solve for t, we just got to bring t sub a over on the right-hand side. So if we do that, we get t, which is really temperature at time t, is a e to the kt plus t sub a. So we want to know, we know what t sub a is, we know what k is, we want to know what that constant a is. So let's start out, let's let t sub 0 represent the initial or time 0 temperature of our object. If that is the case, then plug time equals 0 into this equation, and notice that we get cap t of 0 is a e to the k times 0, because 0 is t right there, plus t sub a. Well, e to the k times 0, that's e to the 0, which is 1. So this is really just a plus t sub a here. And then we want to know what a is, so bring this guy over on the left-hand side as a negative, and you get that a is t of 0 minus t sub a, but t at 0, that's this guy right here. That's t sub 0. So t sub 0 minus t sub a. So now we know what that constant is. It's t0 minus ta. We can plug that back in here. So in general, our solution to Newton's law of cooling is cap T is going to be T0 minus T sub A, that's your constant out in front, e to the kt plus T sub A. So if you want to, you can just use this equation for Newton's law of cooling problems. Or if you want to, you can set up the differential equation with the constants that they give you and work it through. So let's try this on an example. So we've got a dead body that is discovered at 2 a.m. and the body temperature is measured to be 95.3 degrees Fahrenheit. So that's at 2 a.m. And then at 3 a.m., which is 1 hour later, they measure the body temp again and it's 94.8 degrees. So if the room temperature is 73 degrees Fahrenheit, let's find the time of death. So this is our forensics application. So let's lay out what we know in terms of the variables that we have defined, like t sub 0 and t sub a, etc. So first of all, let's bring our equation from the previous slide, which is t equals t0 minus t sub a, e to the kt plus t sub a. So we want to fill in as much as we can of this. So what we know is that t sub 0, that's the initial temperature of the body. Well, you could say, well, the initial temp was 98.6. There's a couple problems with that. We don't know the time for the initial temp in relation to this 95.3. And then also people's body temperature, their normal body temp can vary. Not everyone is 98.6. So let's let the initial temp be 95.3 degrees. And then T sub A, the temperature of the environment, that's the 73. And then what do we do with this 94.8? Well, that's at 3 a.m. So our initial time, we're calling time 0, 2 a.m. So this is going to be T equals 0 is 2 a.m. That's what we're using. And so this is at 3 a.m. it's 94.8, so that's actually telling us that cap T at time 1 hour later, is 94.8. So that's the information that we know. Let's go ahead and plug in here. So if we plug in T sub 0 right here, 95.3, T sub A, 73, and T sub A on the end, 73. So, and then we can combine these two and get 22.3. So it's 22.3 e to the kt plus 73. So now we've used most of our given information. We haven't used this yet here. That's going to help us find the constant little k. So what we know is that t at time 1 is going to be 22.3 e to the k times 1. So we plug a 1 in here for t plus 73. And we also know that that value is 94.8. This guy right here, t at 1, 94.8. So this will let us solve for k. So let's take our 73 and subtract it on both sides. So bring that over as a negative. And that will give us 22.3 e to the k is 21.3. Now we want to divide this 22.3 off both sides. So if we do that, we get e to the k is 21.3 over 22.3. And now we want to undo the exponential to get to the k. So take natural logs on both sides. And these guys cancel by cancellation law. So our constant k is the natural log of 21 22.3 over 22.3, which is approximately negative 0.0458796. So I use a lot of decimal places here because when we're talking about exponential growth, you need accuracy in your constants or you can end up way off in your answers. So let's go ahead and plug in that constant. So now we know that our equation is 22.3 e to the negative 0.0458796t plus 73. Okay, so I just plugged in my k right here. So we already had our other values. So now what do we do? Well, we want to find the time of death. So the time of death will assume that the temperature was 98.6. So we're going to set this cap t equal to 98.6 and solve for time. So take cap t, which is 22.3 e to the negative 0.0458796 t plus 73, and set that guy equal to 98.6. So now we want to solve for little t. Well, this is just an exponential equation. Why don't you pause the video here for a second and solve this out and see if you get the same thing that I do. So bringing the 73 over on the right-hand side as a negative gives us 22.3 with the exponential equals 25.6. Now we've got to divide that 22.3 off on both sides. So we're going to divide by 22.3 here and on the right. So that gives us e to the negative 0.0458796t is 25.6 over 22.3. We want to undo that exponential, and how do we do that? That's right, logs. So natural log on both sides. Natural log and e cancel each other, and we are left with just the exponent, which is negative 0.0458796t, and then we've got the log of that quotient on the right-hand side. We want to solve for t, so we want to divide off this coefficient on both sides. So t will be equal to the log of 25.6 over 22.3, and then we divided by that negative 0.0458796. If you do to two decimal places, compute that, you'll get negative 3.01 hours. So that negative 3, that's 3 hours before time 0. So negative 3 hours, that would be time 0 here was 2 a.m. So that would be approximately 11 p.m. Just slightly before 11 p.m. All right, so now you should be able to try this yourself. Why don't you try WebAssign problem number 4?